那我们开始上课哦，那我们2节课中间就不休息，然后就上完，然后就再下课这样。Alright, so start the class. So first part of this course, please review a little bit of a TSP signal system. If you have forgotten or if you have never taken those courses, look into the slides or look at the textbook. I'll go through some few important key concepts that'll be used in the course in the next few slides. Okay, that's a recap, right? If you have taken signal system, you know this, right? LTI systems and properties. So LTI means linear shift invariant or linear time invariant system. So it's taking basically a system is basically a unique transformation mapping from one sequence or one signal to another signal. Okay, whose input and output relationship can be described by the system. We can analyze the system to properly sort of analyze the properties, how its frequency response, and so on and so forth. So there are a few useful properties. Linearity. Okay. So linearity obeys superposition. So that means if you have a system that's linear, that means if you have two inputs, x1 and x2, two y1 and y2 with a and b are two constants. So the system applied on a linear superposition, x1 signal plus x2 signal, each of them with a constant magnitude, a times x1 plus b times x2. This can be simplified directly on each individual components, okay, multiplied by its constant. Okay, if your system has that behavior, it's called a linear system. So assuming as long as your signal, okay, can be written as a summations of subparts of the signal, the whole system applied to the whole signals can be written as the system applied on individual subcomponents, and then you can pull out that constant in front. Okay. We call that kind of system is a linear system. Okay. Time or shift invariant. So we know y of n equals to some transformation on the signal x. Okay, so the system applied on the shifted version of a signal creates the same shift in output. Okay, we call that the shift invariant for all k that's integers. Okay, so that's if you have a system you can apply on a set of signal. Once you shift the signal, the output shift the same amount. Okay, we call the system itself is a shift or time invariant system. Okay, so we know if you have a system that completely characterized, if you have an LTI system, meaning the system has properties of linearity and time invariance, you know it's completely characterized by its impulse responses. Okay, let's look at this derivation, right? The signal is some transformations on your system applies onto your signal. Okay, your signal always can be written as a summation of x of k multiplied by some shifted delta, right? So again, any signal can be written as values multiplied by shifted delta, basically those sequence of delta, all those points. Okay, summation of those things. Since we know the system is linear and time invariant, so first of all, the transformation can now be inserted into the summation, right? The transformation applied on the whole summation equals to summation of the entire individual system applied on individual subcomponents. That's linearity. So we can push that transformation in. So the summations of the value, okay, the transformation on a signal. Okay, so, and then, we call this transformation, some system transformation on the delta sequences. We write that as an HK of n, okay. We call that response to delta of n minus k. We call this entire thing called impulse response, right? So the system's impulse response. So that's why the word impulse response, because you write your input signal as a summations of impulses. Okay. Once you write in a summation of impulses, your system pushes into the whole formula, and you have these values multiplied by a transformation on the impulse sequences, and we call this impulse response. So your system is completely characterized by its impulse responses. Okay. So we can rewrite this, right, as y of n equals to summation of k minus n to infinity, the signal value at each k point multiplied by the impulse response, which is the transformation of your system applied onto the delta sequences, right, h of n minus k. Now we just give this a new notation called convolution. Okay, so it's this multiplied by h of n minus k, okay, and then you shift this k, okay, and we call this entire operation called convolution. Okay, so if your system is an LTI system, if you know its impulse response, you can take your input convolving with that impulse response to get your output. Okay, that's the properties of an LTI system. Okay, or you can do substitutes of the variables. You can rewrite this as x of n minus k times h of k. Either one works. Okay, so convolution, this operation is a byproduct of a system that has a property of linearity and invariant. Okay, because of these two properties, and you decompose your x of your signal into a impulse sequences, then you can rewrite the output versus the input as though it's output with input convolving with the h of n. Okay, the convolution, the terminology here really comes from linearity plus time invariant. Okay. All right, so this thing we call pulse responses. Okay. Now moving on fast. Okay, so we know LTI system. It tells us if you can decompose a signal into a subset of superposition. Okay, if you have a system that's linear and time invariant, apply on that composition signal, you can work it out by applying on the individual component. Okay, and then sum it up at the output. Okay, so and you can also completely rewrite that as a single mathematical notation called convolution. Okay, let's look at Fourier transform. Okay. What's Fourier transform? Okay, simply we can think about it as basically expressing a sequence, basically a signal sequence, as a superpositions of complex exponential, right? Where the complex amplitudes are determined by the Fourier transform coefficients, right? So again, the ideas of Fourier transform is decompose, okay, your signal, or we call it transform on your signal, okay, or decompose your signal using a set of superposition of a complex exponential. Okay, so you have this signal equals to some values multiplied by e to the j, omega 1, omega 2, omega 3, all those things. Okay, each of the coefficient you can find out by doing a Fourier transform. So you can imagine Fourier transform essentially is a decomposition process. Okay, you can compose your signal by projecting onto the basis or projecting onto the dimensions of exponential, and then resynthesize that. Okay, so x e to the j omega, this is the Fourier transform. The Fourier transform, the coefficient you get for each of the e to the j omega, right, equals to what? Equals to sum over n minus infinity to infinity x of n e to the j omega. That's called an analysis for taking the time domain signal, looking at in terms of e to the minus j omega axis. Okay, and then look at the values itself. Okay, that gives you the transform coefficients. Okay, now you can look at the time signal into a Fourier transform kind of a Fourier basic frequency domain aspect. If you want to resynthesize that, okay, you look at the Fourier transformed sequence multiplied by e to the j omega. Okay, integrating over minus pi to pi, right? Because that's only the region where this omega completes one period. Okay, so you integrate over this thing, divide by normalizing constant 1 over 2 pi, you get back to your original x of n. Okay, so Fourier transform taking a discrete sequence into a continuous frequency domain. Okay, taking a continuous frequency domain back to the discrete sequences. Okay, this kind of thing we call discrete time Fourier transform, right? You learned that probably back in your signal system. Okay, so but just understand Fourier transform, right? Conceptually, you can think about this as a decomposition process, taking a signal decomposed using exponential signal. And why use exponential as your basis to decompose? Because you want to look at its frequency content. Okay, so you want to transform the time domain into the frequency domain. The magnitude tells you sort of how much amplitude or how much component of your original time domain signal is in the frequency, that particular frequency beam, right? And then across all different frequency beams. Okay. So we know mathematically, convergence of this kind of convergence has to happen if this summation is absolutely summable, right? If this summation goes to infinity, then you don't have an actual Fourier transform. Okay, so there's some criteria. You want to make sure your signal is a well-behaved signal. It doesn't, when you sum it up, it doesn't go to infinity. So the Fourier transform itself requires the signal has a good property, okay, which is absolutely summable. But for our practical purpose, right, the signal we deal with in everyday life, you record a signal of my speech, okay, 1 second to 5 seconds. Is that absolutely summable? Of course, because there's finite, okay. When you sum up the value, it's less than infinity, right? So many practical signals that we've designed that we see in real life, they are absolutely summable. They always have a Fourier transform exists. Okay, so Fourier transform to be absolutely convergence, okay, to a continuous function of omega, right? This is a digital frequency omega. Okay, so digital time, okay, discrete time, okay, will do a Fourier transform and give you a continuous time, like a continuous frequency in a frequency domain. Okay, so absolutely summable in X of n in a time domain basically means it has a finite energy. Okay, so there are a few sequences that have finite energy, but maybe not absolutely summable. Okay, for example, a sinc function. Okay, it's always oscillate. Okay, those sinc function will also have transform. Will have Fourier transform. Okay, we won't go into the details. They're probably something you have learned back in the days. Okay, so how do I do a Fourier transform on a sinc function? All those things. Okay, so you apply different convergence criteria to make sure those Fourier transform also do exist. Okay, for all practical purpose, in terms of speech signal, right? We can think about the signal itself. We can analyze it from the Fourier perspective because you are decomposing the signal itself, okay, into a set of frequencies. Okay, then by understanding how my signal as I represent it in terms of different frequencies, I can know the properties of the signal, right? Is it a high frequency signal, low frequency signal, high oscillation, low oscillation? And that's also very important in terms of understanding speech. We'll also talk about that component later on. But Fourier is this is a mathematical tool, but that helps us to understand a physical signal that we produce, which is the speech signal we have. Okay. Now think about Fourier transform and convolution. Okay, we know LTI system. If you have a system, you have a convolution of the system with your signal, then you have the output. Okay, so then let's repeat. Okay, Fourier transform of the convolution sum. Okay, y of n. Okay, again, this is convolution sum. H of n minus kx n. Okay, we know yn equals to some transformation on x of n. Okay, x of n we can rewrite that as a synthesis function, right? We resynthesis back from the Fourier transform domain back into a time domain. So some system apply onto 1 over 2 pi minus pi to pi x e to j omega e to j omega d omega. Okay. This is a some value, push it out. Okay, some integration. The system apply on a particular sequence, right? This is a T is a system. Okay, it applies on a sequence. Out of all these things, which is a sequence, this is a sequence, right? So your operation apply on here. So 1 over 2 pi minus pi to pi x e to a j omega, the transformation, your system apply onto e to a j omega d omega. Okay, now we can rewrite this, right? A transformation on a signal, right? On this particular signal, which is a to the e to the j omega times e to the n, sorry, e to the j omega n. Okay. So rewrite everything 1 over 2 pi minus pi to pi x e to the j omega h e to the j omega. What's this? This is essentially y to the e to the j omega. And this is minus e to the j omega, right? Because this becomes a resynthesis, right? A resynthesis equation for y of n, right? So y of n equals 1 over 2 pi, 1 over pi minus pi to pi, x e to the j omega, h e to the j omega, e to the j omega n. Okay, so this is itself a resynthesis equation for y of n. So the y of e to the j omega essentially is this. So we know y of e to the j omega equals x e to the j omega multiplied by h e to the j omega. So a simple derivation tells you Fourier transform has a nice property. Okay, well, it takes convolution sum in a time domain into a product. Okay, so originally it's a complex form like this, a bit more complex. Okay, but in a Fourier domain, then becomes a multiplication. So your x signal for each of the omega coefficients, right, multiplied by the h of the signal of e to the j omega, each of the coefficients. So the response of the LTI system to each complex exponential in the Fourier transform, this is the formula for x of n, is obtained by multiplication of h of n. So linear systems again allows superposition. So again, with this, you can basically see that your x as it represent in the Fourier domain, each of the omegas essentially get filtered by your impulse responses as it represent in a frequency domains, and then they just multiply, get your final output of your signal in the Fourier domain. Okay, then you come back and you get your time domain. you're designing a system, that's when back in the days when you learn signal system, you're designing filters, designing coefficient, everything in the frequency domains, because you're looking at your actual e to the j omega, what's the responses of with respect to each of the omega, so that it's going to change each of the omegas within your time domain signal by multiplying these two. Then you get your desired output. Once you get your desired output in the frequency domain, then you quickly back to the real life, the original time domain, you get the final output. So you design this kind of thing to make sure each of the x is being decomposed as each of the frequency signals, how that's going to be modulated by how your impulse responses, each of the omega is going to modulate each of the subcomponents of your x. Put it together becomes your output. Okay, so it's a very nice combination. Okay, a very nice combination. So thinking about linear time invariant system, right? Linear time invariant system tells us decompose the signal into subcomponents, linearly summable subcomponents. Okay, that your system can operate on individual subcomponents. Fourier analysis tells us you can decompose any signal using complex exponential sequences. Okay, so combine these two, we're saying we can decompose a signal using complex exponential sequences. If you're designing an LTS system, then all you need to figure out is that LTS system, how it operates with respect to each of the signal and its frequency bits. Okay, then you have the proper properties of your system and you have the proper properties of your final output. Okay, so basically it's putting together this kind of a transform LTS system convolution all together. Then you can see basically there's a link between all these things. Okay, we can decompose this thing into a complex exponential. So we know a signal has certain low frequency component, certain high frequency component. You can design your h of e to the j omega, some filters, low pass, mid pass, high pass, band pass, whatever you like. Okay, and you multiply the two, so you know your signal can be decomposed as complex exponential. Each of the complex exponential is going to be modulated by each of the complex exponential in your design filter. Multiplying the two, get your final output. Okay, to an inverse response, to an inverse transform, then you're coming back to the original signal. Okay, so many of the systems, many of the ideas that we think about, this kind of thing will be important in terms of speech processing. Okay, we imagine signal that's being produced. Okay, through our vocal tract or our system. Basically, it's a source, it's a system that finally produces sound you hear. Then we can try to analyze those source or the system using some kind of Fourier analysis and LTS system that we will develop. Okay, so the link will be there, but these are general mathematical tools that you can manipulate to understand. They're basically, I want to say, they're basically two major concepts: superposition, decompose any signal into a sum of subparts. Linearity ensures that the system operating on the system can be individually operated. Fourier tells you the signal can be decomposed as complex exponential. So it follows that linearity superposition idea that you can design your system to operate on every individual complex exponential. So you can have a desired frequency output as you design your system. Okay, so these are major concepts to keep in mind. The next thing I want to talk about is this digital world sampling issue. Okay, again, this is also review probably from the DSP as well. So I want to talk about the properties of sampling, right? Once you sample a signal, what happens? Okay, and then this is radical because when we use microphone nowadays, you have a sampling rate. Okay, the digital signal has a sampling rate. So doing a sampling there or you process within your computer, that also means there's certain sampling that's already happened. Okay, if you sample a continuous weight pressure coming out from my mouth, okay, that sampling the signal you record, okay, what property have changed, okay, and stuff like that. Okay, so XALT was called analog signal, continuous in time. Okay, the 1/2 pi minus e to the XAJ omega e to the j omega t. 也有别的说话吗？我有点诡异。OK， anyway， 抽到别的讯号断了，超级诡异。OK，anyway。All right, so these are continuous time Fourier transform. Right? This is the inverse formula for continuous time. 有人跟我讲话。
我有去去那边啊，小房子，
隔壁
好好，
这个有它还是有声音。
是那个音响，
Stop。
嗯，
好，那到下面讲好，
讲旁边有李老师。
可以，过去的对，英文好不是做辅助，
英文做辅助。你可能是楼下，我觉得可能楼下。还是我去找个换一下。你去5楼问一下那个设备。对，但很多这个问，这个我就把它关掉。Okay, I'm going to try to speak it. Okay, not loud enough, let me know. So anyway, this analog signal 1 over 2 pi, right? We can inverse transform from the continuous sine Fourier transform. So anyway, so if you have a discrete sequences, right? So once you sample a discrete sequence, the inverse is 1 over 2 pi x e to the j omega e to the j omega, where x is the forward transform, x e to the j omega equals the finite summation. This is the infinite integrations. Okay. So let's rewrite stuff. Okay. X s of t. Okay, let's write it as a sample gas sequence. Okay, so originally you have a continuous time, right? Continuous signal sampling means you take in points from the continuous time, okay? And those points can be indicated by endpoint, right? So first point, second point, third point, fourth point, fifth point, okay? The length between the point you take a signal out of xs, we call them sampling period, right? So you can write x of t equals x of n, right? So basically it's indicating which point that you're taking, which integers you're taking. Okay, we write that as in the original analog signal, which is x, a, and t, right? So t is your sampling period. Okay, the first point, second point, third point, fourth point, right? So x, a, of n, t. So basically that means x, a equals x, a of t at t every integer point of nt, 2 and t, 3 and t4, the 0 other ones, right? So this is called a sample sequence. Okay, t is the sampling period. Reciprocal, that we call it sampling rate. Okay, omega s equals divided by 2 pi. Okay, so that's okay. So we know I want to talk about sampling, not for a sampling purpose, more for a purpose of what happens in a frequency. Okay, so if you probably recall back in the day, so you sampling in time domain, you create a replication in a frequency. So every signal repeats itself every 2 pi. Okay, so yeah, because of this sampling. So can be shown that the Fourier transform of the sample signal x of s e to the j omega t equals 1 over t summation of r or minus 1 to infinity. This original analog signals its Fourier transform, and it'll have a replication at every j times 2 pi r is an index integer divided by t. Okay, so once you sample the signal, okay, if you look at that signal in a Fourier domain, okay, what happens is within every sampling period is a complete version of your original xa j omega, okay, which is the original continuous time signals j omega, but it's going to create replication, okay, at every this 1 over t or pi over t, this interval will create a complete replication. Okay, so consider this x of a to have been limited omega naught, okay, such that omega equals to w divided by t. So you can have two cases where one of the cases called an alias, which is omega naught over t is less than pi over t, or alias where omega naught over t divided by 2 is greater than pi over t. This is your intervals where you have a replication of your original frequency. If original time domain signal has a bend, okay, that means its frequency, that time signal in the frequency domain has frequency components beyond, okay, your sampling periods, that intervals, okay, then you create alias. Okay, so that's what we call aliasing. Let me see if I have a plot shows better version. So this is XCOT, right? It's an analog signal that we see in any real life. Okay. If you take this Fourier transform, continuous time Fourier transform, if it's a band limited Fourier transform, you get this thing. So no signal outside a particular band. It only has signal here. If you take a sampling of these things, right, every delta t, okay, so every time period, the 1 over that would be the sampling rate. So every such point, you take a point out of this signal. Okay. What happens here is, again, you have this thing that's scaled by 1 over delta of t, and it repeats the same shape at every 2 pi delta t. Okay. So if this thing is greater than this pi over t, then this thing will alias, or this thing will merge together. Okay, you don't have a original replications of what the signal is. So this has to be very careful, right? So once you sample the data, okay, the data you sample is going to create a replication. If your signal span is limited, that's fine, okay, and limited to a certain degree that we call Nyquist rate. If it's limited in a way that doesn't create aliasing, it's easy to repeat the signal by simply taking this part out and zero everything else. Then you have the same signal as your original analog signal. But once you do a sampling and this thing alias, okay, then you no longer will give you back your original signal in the physical world. Okay. So for all practical purposes, right? So many of our real world signal it will never be limited. Okay. So the joke I always say, right? So whenever you do digital signal processing, as long as you do sampling, okay, you're working on a fake data, okay, because it's never the same as you see in real life. Okay, as long as this thing is not completely band limited. So a lot of signal we have here in real world is never really band limited. We assume it is, or we try to make it as band limited, okay, but in reality, okay, they're usually not band limited. So just keep this in mind, okay. Sampling is a necessary process to process everything in computer. So your MP3s, your sound file, everything, okay, there has to be some sampling that happens. Okay. That sampling needs to be at a certain rate to make sure if you have a band limited signal, it can fully reconstruct, and that's the rate we call like Nyquist rate. Nyquist rate. Your sampling rate is at least twice the highest frequency of your original analog signal. Then you can fully recover your original signal. Okay, so it's pictorially as long as the number is at least twice, okay, the highest point here, then this point will move into here, this point will move into here, and you can easily reconstruct the original signal. Okay, that's the basic idea of Nyquist theorem. So you just want to sample at least twice the highest frequency. So assume speech, okay, a human can produce at highest, okay, 20 kilohertz. Okay, we cannot hear or we cannot produce beyond this frequency. So you can design your sampling to be 44.1. Okay, so that's probably also the highest sampling rate you see in any audio file. So because divided by 2, okay, you get 20. Okay, so almost all the signal we are able to produce or perceive, okay, already beyond that, there's nothing there. So you can design your sampling rate based on the physical property of the signal that can actually be transmitting frequency. All right. So another thing is to know the duality. Okay. Sampling in time creates periodicity repetition in frequency. Okay. Sampling in frequency. Okay. What happens is going to create periodicity in time. Whenever we do, what happens, like in what situation we do sampling frequency? Basically everything, right? Because once you process in computer, you use MATLAB, you use Python to do fast Fourier transform, FFT, okay? You store those values, those are discrete values. So what happens, you're not recording a continuous frequency spectrum, you're recording a discrete set of frequency and their coefficients. Okay. So essentially what happens there is you're doing a sampling in a frequency. Okay. Once you're sampling in a frequency, what happens actually creates a periodicity in a time domain. So if you don't sample this fast enough, okay, it would have the same issue as you create an aliasing also back in the time domain. So this duality just to make sure. So every time we do sampling, every time we discretize stuff, okay, discretization.
老师他们是说，因为现在没有要临时改频段，所以要的话，我们可以先去借210教室来用，或就继续这样。
就先继续这样。OK， 这可能到了啊，再请。The same what I say, okay, the discretization, okay, discretization of anything, okay, either in time domain or frequency domain, it creates a duality as a repetition periodicity in other domain. This is this by math, okay, there's no, cannot work it out, okay, this basic sampling in time create a periodicity in frequency. Sampling in frequency creates a periodicity in time, okay, so you want to make sure sampling, you want to sample fast enough in time, also want to sample enough points around the frequency axis so that it can faithfully re-represent the time domain signal. So these are two sort of major things. Okay. So again, originally we don't have a continuous continuous signal. If you do sampling, okay, these are discrete signal you record your computer, your microphone, whatsoever. Taking a Fourier transform, what you'll see is some repetition at every 2 pi, okay, the same properties. Now, because you don't record all this in your computer, all you do is plot these points, right? Take 512 FFT over 2 pi, right? So that means you have 512 points around here. So you're taking points around this curves, continuous curve. What happens in the time domain is that it creates a repetition at every n points you sample around here. So if it's 512 point, you have 512 point here, 512 point here. These two are the same repetition. Okay, so if you have a signal that's originally 512 points, you only look at 256 point here. Then you have about 250 points will be erased. Okay, so I want to make sure that the duality, keep in mind this is what we do in real world, right? So you record this signal, okay, you do Fourier transform, Fourier analysis. You do all those things in this domain, okay. But what happens is we're actually looking at this signal, okay. We're trying to analyze this signal as though we're trying to analyze XAOT, that analog signal that's producing from my mouth, right? Record it, digitize it, do a Fourier transform, discretize it, and look at frequency property, and you say, oh, hey, there's there's signal in 500 hertz, 600 hertz. What effectively you're doing is actually analyzing this signal. Okay, not the signal that was originally that continuous time waveform. Okay, just keep this in mind because there are some issues around this when we're actually designing some speech analysis tool. Okay, to try to analyze it in frequencies, trying to cut a window here and there. So there are other issues would appear. Okay, when we start analyzing speech signal, originally as an analog signal data, we're using the digital tools, discrete tools to analyze them. Okay, so anyway, so you should probably know about this as well. Okay, so Fourier transform, if you take sampling in time, you get discrete Fourier transform. If you do a sampling and frequency, then you finally what got is the discrete Fourier transform. If you make discrete Fourier transform really fast, then that's fast Fourier transform FFT. Okay, so for a finite duration sample signal, you can imagine it's taking the DTFT with n periodic signal, sample in frequency domain around linear circle, and remember duality in terms of time frequency sampling. So let's use more practical engineering application in terms of speech analysis, discrete Fourier transform and fast Fourier transform. When you apply that thing onto a signal you record, okay, you want to make sure you understand the implication you actually injected into a signal. Some periodicity will appear. Okay. The number of points you sample around that will create either alias or non-alias version of your signal. Okay, but anyways, in real life, we always do many assumptions. Okay, very limited assumptions. Okay, finite durations. Okay, those things are practically actually when we operate on signals, so we take a small chunk of signal every 5 seconds, every 20 milliseconds, and try to analyze it. So it's finite duration. Fourier transform exists. Okay, We have a certain assumption. We know human speech is band limited, so there's a way we do sampling to make sure we actually get the right amount of number of points, okay, and so on and so forth. So know the mathematical implication. Of course, when you do engineering coding tools, it's always very standard. Just do it and as though this thing never appears. But mathematically knowing the implication is important. Okay, so summary notes about the DSP parts of the course. So you want to understand speech signal, okay, as recorded through microphone, essentially a sampled version, for example, 44 kilohertz of continuous pressure onto a microphone receptor that has a finite duration. That's a signal that speech signal processing people, they operate on this kind of assumption, right? Your pressures out of your mouth recorded by the microphone receptor, okay, and digitize it by sampling it, okay, usually sample it highest at 44.1 hertz or 44 kilohertz. And you don't record it continuous, usually it's finite in duration, you record only a certain amount of seconds. Okay, so all digital signal processing errors that would occur in such a signal happens to speech signal, right? Sampling create periodicity in both in time and frequency. Finite duration, again, we'll touch upon this a little more, please. When you have a signal in continuous, okay, think about continuous Fourier transform. It's summing from minus infinity to infinity. Okay. You take a small chunk called finite duration. What does that mean? That means you apply a window function onto a continuous signal. Okay, a window function, and you may not thought of it, right? You just think, okay, I'll take seconds from 1 to 5. What it means is you apply a rectangular window, okay, from second 1 to 5. Everything else 0, and then retrieve 1 to 5. Okay, when you apply a signal to another rectangular function signal, the thing that's been left, okay, it is these two multiply, right? So when you look at what's that left in the finite duration signal, look at the frequency component of that. It's not the same thing as the original signal because you have a function applied on the original signal. Okay, so we have finite duration. Okay, the finite duration is a nice word we think intuitive. Take a few seconds. Mathematically, you can have to think about in terms of Fourier transform. Like continuous Fourier transform, you apply another rectangular function. These two functions output becomes the new data you analyze. Okay, that data and the frequency component within the data is not the same as the frequency component of the data within the original signal. It has been modulated by that rectangular function that you have chosen to apply onto. That changes the property, and you no longer are working on the original speech, which is the pressure comes out of my mouth. Okay, so again, know all this little implication here. Okay, so later we'll talk about in speech we spend quite a bit of time designing that windowing function. Okay, we want to make sure the windowing function design doesn't distort the speech sound too much. Okay, so that we can still properly analyzing the speech signal. So these are important. So understand, some of the sort of intuitive or very, no-brainer kind of trivial operation that we do on signal, it changes the signal's property. Okay, completely. So you're not really looking at the original signal to analyze that original signal. Okay, so there are all these engineering parts. Okay. Of course, we'll talk through all this, understand all this basic issue in terms of DSP. Realizing a lot of these issues are practically solved using higher sampling rate or a proper design of a windowing function to mitigate some of the issues. Okay, we'll talk about those things. Okay, so if you want to review notes, you'll talk a little bit more deeper about convolution, circular convolution, Z-transform, and other things. Okay, these are different techniques in a way to try to analyze signals and time frequency properties. Okay, but we won't go into detail in this course. Okay, let's move into the more speech part of thing. Okay, that was DSP. Okay, signal system and so on and so forth. Let's move into the speech. We'll talk a little bit about the knowledge around how human produces speech, or we call speech production. Okay, remember last time we talked about understanding speech. There are two aspects: speech production and speech perception. How we produce speech and how we perceive speech. We'll start by talking about what we know about humans' production, speech production. Okay, human speech production. Okay, these are voluntary movements of your analytical structures. We call it articulator. Okay, which is basically your vocal tract system. Okay, vocal tract system has different subcomponents. I'll show a cross-sectional view later. Okay, the glottis, pharyngeal cavity, and oral cavity. The vocal tract system length, male a little longer, about 17 centimeters, female 14 centimeters. Cross sectional is about 0 to 20 centimeters square. Except for the vocal tract system, we also have a nasal tract system. That's when you get cold, the sound differs because there's a different resonance structure creating. But that resonance structure also in combination with your vocal tract, these two create a resonance to produces the speech. Okay. So the nasal tract system, nostrils, phylums, the length is about 12 centimeters, cross sectional 0 to 5 centimeters. This is sort of cross sectional. This is the nasal. This is the nasal tract system. And this is the vocal tract system. Okay, and then go down. This is the lung. Okay, so the lung expels air through your vocal tract system. There are different articulator and muscle movements. Okay, that creates a resonance structure, and the air starts coming out. And here it's connected, right? So it creates additional resonance structure within the sound actually expelled from the lung. Finally, through your lips and your tongue is doing a lot. Okay, if you imagine, or you show a little video, your mouth move, your tongue moves so much during your speech. Okay, and that finally shapes the entire sound that we can produce, and then finally out from our lips. Okay, so basically that's on high level. Okay, lung expel from the lung expel air. Okay. So there's a vocal fold. Okay, vocal fold is a closing and opening that creates a little bit of periodic structures within your sound, and that goes through air as it goes through and hits or changes because of the muscle movement, hits or changes and creates a new resonance, modulated by the nasal systems or create additional resonance. These two things hits your tongue. Okay, your tongue keep changing. Make sure it hits the right. We call it articular gestures, right? You say your mouth has to stick out, right? If you don't stick out your tongue, you cannot pronounce. Okay, so your mouth tongue has to move quickly, make sure all those sound units are being hit properly, and finally that's how on high level we would do this. Let's see if I can.
These are the movements that show the C sounds.
Here's see here is for the opening, closing. This oral articular, you can move your muscles. This is going to your oral cavity, and you see your tongue keep changing. Okay. And you can probably see also more clearly in this singing. Okay. Maybe the tongue like hitting I can't see there's a vocal for opening, closing. Your tremulous muscle creating resonance structure in your hits all this gesture so that you can produce this very nicely of this sound. Okay. So these are very for humans, these are very articulated movements. Okay, very difficult. Okay, so that's why kids take a little bit of time to finally they sound like they can talk. It takes quite a bit of time to make sure all these things are coordinated in a way, and super fast. Okay, so it's not like you're slowly stringing together words, right? You're just stringing together words. Okay, all these words has to be come out sequentially and then fluently. Okay, and what's more complex is the way we piece all these things together. We piece in a way that's semantically meaningful. Okay, it carries message. It's not just random. It's not just random sound you actually say. It's actually a language that we're ordering that creates a message that I want to tell you. This lecture, the mouth movement is like this, right? So I'm creating a language so that I can show you the actual content, but at the same time, your mouth has to do all those things together to make sure those sounds are hit correctly. Okay, so many things are happening. So we only talk about high level, but really there's very little in terms of even current nowadays speech science. We know something about speech production, but not a full pictures. Okay, it seems very complicated on how we actually learn to speak. Okay, in a way that coordinating so many things. Okay, so fast, so quickly.
to always hit the right target. Okay, you don't question about yourself saying the word I, right? But think about, putting I in every sentence. Every time you want to say that, your mouth has to quickly move to that position and pronounce I. Okay, that's a very non-trivial ability that we humans are capable of doing. Okay, right. So let's do some simplified model of speech production. Okay, these are things that we can understand. Okay, so the acoustic waves at the lips when the air expelled from the lungs get modulated, and there are two cases get modulated. One is called the vocal cord tenses. Okay, so when it things tenses, the airflow as it runs through, it creates a vibration. Okay, and the second case is vocal cord relax. So the muscles don't get tenses, so it can go through. Okay, when it hits something, okay, it creates either a turbulence, so you have a turbulent sound, or it hit a closure, and your pressure build up and then release it, and you get a sound like but, right? You cannot pronounce word but without closing your mouth. You have to let that mouth close, build up the pressure, release it. Okay, so and then there are other sound created. So few cases, right? Vowels are used there, we call the voice sound. Okay, so that's when your vocal cord tenses. Okay, your airflow causes it to vibrate. So you say touch here. You can touch the vibrations happening here. Okay, you produce a sound that you can touch it. There's no vibration. Okay, it's basically a relaxed vocal fold. Your air goes through. It somehow hits your vocal tract and then generate that sound. Okay. You want to have the stop sound, right? Okay, a lot of those things you have to hit something that completely close it and release it. Okay, so you see pressure builds up and release it. Okay, so we are humans were quickly, generating all different articular movement to make sure all these sounds are being generated properly. Okay, so these are broad categories of ways we generate sound. Okay, so a very simplified model of thinking about this entire speech production problem is called the source and filter model. Okay, it's back in probably proposed back in the days in 1970s or so. It's a very nice concept to understand the whole speech production. Okay, it's a very simplified concept, but very nice concept. Okay, so source and filter model, it tells us there's a serial connection of three independent functions that we human uses to produce a speech. Okay, there's a sourcing part, there's a filter part, okay, there's a radiation part. Okay, can you imagine those are connected tubes? Okay, muscle forces, right, pushes your lung, right, lung expels air, okay, through your vocal pores. Okay, this will open and close or tense or relax. Okay, the thing will go through the air, start to hit. Okay, the vocal tract, either some kind of constrictions or stops, and then virginal cavity. Here, Villa, that's the opening from the nasal cavity to your mouth cavity. Okay, creates additional resonance. Then at the mouth, and then you have the tongue. That's either touch here, right? Creating different sound. Finally, at the mouth outputs, your lips creates a different again modulating even further. Finally, with the thing that we reproduce. Okay, we imagine this entire system, speech production system, has a source, right? Meaning just the air pumping out through here. Okay. Depending on this opening and closing, it creates a vibration or let the air through. Okay, we have this filtering function. Okay, some tube reconstruction. Okay, that creates think about water bottle. Okay, you blow into a water bottle. The way you blow, that's your source, right? The shape of that water bottle. Okay, with different shape, it creates different sound. Okay, finally at the sounding output, then that's your radiation. You can imagine these three things are three connected independent components get stringed together to make it our speech production system. On a very high level, we can think about that. Okay, so I'm sorry. So the idea is the source gives you information on how the input to become the sound. Okay, if it's voice or unvoiced, or how fast or the thing, or like male and female, we have different muscles here. So some of our male's frequency will be lower, female's frequency will be higher. Those are non-content based stuff. Okay, your filter function creates that final sound, for example, ah, okay, ah is the sound you hear, ah, okay. So it's a air that pumps through your particular configuration of your vocal tract. That vocal tract create that ah, okay, final itself. Okay, so imagine this source, right? The way we start, putting into a system. That filter is a system. Okay, the system creates a final ah, because ah itself maybe has a frequency at 400 hertz and 600 hertz. Okay, so basically your vocal tract will configure it to make sure it has this two resonant peak at those two locations. And how to excite this resonant peak? You have excitation, which is your source, which is your air coming out from the lung. So back in the days, people take this system, signal and system perspective into understanding speech production. Okay, you have a source exciting a system that generates a sound here. Okay, that system will modulate the frequencies. Okay, so that you finally hear ah, e, where, oh. Okay, the source will create the high or low frequency kind of stuff. Okay, so that these two combined is finally the thing that we hear. Okay, so that's a very simplified assumption, and this simplified assumption basically runs through the entire approaches of how we analyze speech signal. Okay, so we'll cover a bunch of speech analysis tools that basically build on these assumptions of source filter function. Okay, source filter model of speech production. Of course, there's some justification. Your gloss has a higher acoustic impedance than the vocal tract. Vocal tract has a higher acoustic impedance than the open air. So essentially, these are three different independent components that that are being stringed together. Okay. All right. So next thing I want to talk is on characterizing speech units. Okay, we know roughly how we human produces sound, right? Now we think about the concept of sounding unit. Okay, when we say we're able to produce a sound, what sound are we producing? Okay, we're producing ah. Okay, that means there seems to be a category or seems to be a way of describing different sound. Okay, that's why we say ah, e, well, right? So these are different sound we can make. Okay, so those knowledge comes from linguistics. Okay, so touch a little bit on the linguistics. So how do we characterize speech sound into discrete units? Okay, these are key concepts so that eventually speech recognition can be done. Okay, because again, repeat speech recognition system taking speech sound, mapping into discrete unit of sounding stuff. So we need to first know what do we mean by speech distinct units. Okay, what are those? Okay. So okay, imagine speech as a sequence of sound. Okay, and this sequence of sound we call them is string together using what we call primitive units of speech sound. Okay. Okay, is it true? We don't know. Okay, works fine. Okay, meaning do we really have finite unit set of sounding unit everybody learn to string together? Maybe not. Okay, but that's a good approximation if we assume a continuous speech sound is a discrete set of things that we string together. Okay, that makes things operational. Okay, we can understand it better. Okay, sorry. So yeah. So linguistics using this methodology to study speech sound. Okay, they found that every language has the phone or we call phonemes. Okay, in terms of describing the most basic sounding unit in English, depending on which system you look at. Okay, there are different systems describing different sounding unit. Okay, it ranges from 30 something to 40 distinct unit. What does that mean? That means under a particular system for a particular language, okay, every word within that language can be put together, okay, in the pronunciation using that 40 phonemes. Okay, so there are only 40 unique sounding units a language or a person can produce with respect to that language. Okay. Again, if you think about this process, that makes the whole study easier, right? Because we now originally have a continuous measure of pressure of speech signal. Okay. Now we say, okay, try to understand the speech aspect, speech sounding aspect of those things. We can say, okay, for this particular language, there are only 42 ways, okay, we can utilize our articulator to make sound that are distinct. Okay. So now we just can analyze, okay, how do we pronounce ah, e, u, right? Now we can start studying at least one of the units, how we produces that sounding unit, and then we can have a system describing, okay, if you want to sound ah, if you want to sound e, you want to you want to sound bird. Okay, how we move articulators. Okay, those things. So we're taking a sequence of infinite possibility into a finite set of describing the way we can produce a speech. Okay, so this kind of transformation knowledge from linguistics is very important and also a key enabler for eventually engineering application to come in. Okay, because this is finite set, it becomes easy to do. Okay, if it's infinite set, then you have no way to do things right. It's finite set, then you can say, okay, this signal belongs to one of those things. Okay, then it becomes easier to do recognition and so on. Okay. So the sounding unit can be describing based on the source function, right? Either it's fluctuating flow or fluctuating pressure, the filtering function, the filter function between the lips and the source. So there are types of sound that can be characterized by the sourcing function. There are voice source or unvoiced source. Okay, voice source, that means those sounds you have puffs of air released at a glottis. Okay, you release X number of puffs per second. That's your fundamental frequencies. Okay, so they're also periodic with each period of t not 1 over enough. So things like you and all those vowels, those are voice sounding unit. Okay, where your vocal tract actually release puffs of air at a more periodic structure. Okay. Then creates resonance, okay, with a certain configuration of your vocal tract and create the final sounding R. Okay, those type of sounds we characterize using their source function, because when the source is voiced, then we call those voice sounding units. All right, so usually in the speech science, they approximate that using some kind of function like this. Build up, release the pressure, build up, release the pressure. So our F naught is approximate or fundamental frequency. Basically, we call our pitch, right? Everybody, female has higher pitch, male has lower pitch. Okay, that pitch is to every individual. Okay, but nothing to do with the sounding unit. It's a source, right? It's pumping air into a system. That pumping air has a frequency. Okay, so male has a much lower frequency that we can pump the air to because our muscle stiffness is more stiff around the vocal cord, so our movement is slower. Okay, so that periodicity becomes longer. Okay, so because of the male articulator structure is different from the female, so that's very physical. Okay, so our fundamental frequency is about approximately related to 1 over 2 pi k divided by nk, the stiffness of the vocal cord, m is the mass of the vocal cord, and f naught, this kind of fundamental frequency is related closely to how we perceive the pitch. Okay, again, repeat, in your mind, you should always keep this thing. Production perception is not the same. Okay, we're talking about how we produce speech. Our vocal cord has stiffness and mass. As everybody's different, so you create puffs of air at a different fundamental frequency. Now, if you ask people to listen to that sound, okay, that will be if you can have a higher movements of. If you ask people, do you think there's a higher frequency or lower frequency? It'll be related to higher frequency. They are not one-to-one, but they are very highly correlated. The way that we are able to open our vocal cord faster, okay, when the other person listens to me, it'll make it sounds like I have a higher pitch or pitch. Okay, but this only is approximate. Okay, it's not one-to-one. If you there's people study, okay, those singers, okay. Singers, male singers can sing very high note, okay. It may not be because these are the same, like they also have stiffness, they have mass around it. But they're able to manipulate their articulator to generate a certain kind of resonance so that your perceived pitch will sound higher. So, singing and then, singer, professional singer, there's a different story. But generally speaking, okay, the way we speak, okay, our stiffness and mass in our vocal cord will generally be related to how other people perceive our pitch. Pitch is very important psychoacoustic measure. Okay, tells you about your intent, emotion, and so on. So, if you want to ask questions, you will raise your pitch toward the end of the question. Okay, that's a signal we give to other people that we intend this to be a question, not a statement. Okay, whenever you raise your pitch toward the end. So pitch itself is a very important cues that you actually generate for other people to listen. And also many people have health issues around their vocal cord that will sound different. They cannot articulate better. So those are also issues. Okay. But keep this in mind. These are sources. Okay, so yeah, for middle frequency, males mean about 80, maximum 200, female 150, 50, average about 200, children 200 to 50, 500, mean about 300. Okay, yes. All right, another kind of source called fricative source, okay, caused by tubular air jet from a vocal tract construction somewhere between the vowels and the dips, striking obstacles downstream from the constriction, for example, T. Okay. So again, so there's part of the sound that we would open close, so that creates periodicity, then that creates a resonance component, and with a particular configuration, you say I. There's some part of the sound that we make, okay, you just simply let the air out, okay, but you hit something in the middle, okay. The things that you hit, okay, it creates a different sound, okay. So there are primitives, this kind of sound stops, the one that's easier to understand, right? There has to be some closure, okay. All those things, right? Either your tongue or your mouth has to act as that closure to make sure it builds up and stuff, but there's no vibration here. You simply let the air out. You push the air out, it's a constriction, you close it, and you release. You directly have that sound. Okay, so those are some and air fricatives, the light fricatives and not fricatives. Okay, so this kind of categorization tells us another set of sound that we make. Okay, even through this kind of vibration, it's kind of unvoiced sound, but it's called as it hits some constriction along the way of your vocal tract, it creates the sound you find here. Okay, and there's also some aspiration source like turbulent air jet from the clouds striking against false vocal cord or apparatus. Okay, right. So these are this kind of sound. It has a different kind of sorting structure than the other ones. Okay, so generally speaking, okay, if you want to characterize, right, we say in any language there's a finite set of sounding unit we can produce. English like about 40. Okay, then we can say okay. Let's try to characterize those 40 sounds. A subset of them are voice sound, okay, meaning the sourcing functions of those sound production mechanism are from periodic pumps, okay. Or unvoiced sound, okay, basically some obstacle creates local pockets of rapid high varying pressures. So you have a spectrum of radiation relatively flat elsewhere. So once you hit that. When you hit the obstacles, it creates suddenly some high variation of these waves, okay? And then eventually you release a sound. Okay, so if those are a voice sound, it's voice sound and voice sound. That's sort of kind of broad characteristics. Okay, anyways, just keep there are a lot of things. These are very detailed, but I think on a high level, okay. First, remember a source and filter model is a very good approximation of how we understand speech production, okay, meaning you excite your system. Your system is your vocal fold system, vocal tract system, okay, combined a little bit with nasal system, okay. That filter system will shape the resonant structures of the sounding unit, okay. But what pumps the air into the thing, right? It can pump it into the air. That's the source, okay. That pumping structure can be periodic or simply just some air goes through and then hits some obstacle, becomes like white noise kind of stuff. Okay, so the white noise combined with the filtering function creates sound like the periodic puffs, right? Creating a water bottle shaking has a resonant frequency at 400, 600 that creates the sound ah. Okay, so you can almost characterize each one of these distinct units into the source and filter function and has a relationship so that we know the whole speech production mechanism are kind of like that. Okay. So just a common mathematical function that people like to use in speech production studies. Right? If you think about excitation source, the input or the source in terms of signal system, right? If it's a voice sound, we use white or random noise. Okay. If you think about it as a voice sound, we use periodic pulses. Usually it becomes cosine. Pulse sound version basically is this stuff. The filter function, okay, the actual thing that shapes the sound, the characteristics of the sound, okay. The good ones that we'll teach as well is called OPO model, okay. Another word for that is a linear prediction model. It's a model that basically learn where the resonant, where the poles are, right? The poles are where the frequency jumps, right? So the OPO model is a good model to approximate using a linear set of filters to understand the vocal tracks. But OPO model is not good for nasal and frequency. Okay, it works well for RE waves and vowels. Radiation, in speech analysis, we really don't really use it, but when we try to understand real human speech, okay, there's some version. Basically, it depends on the velocity of the sound sampling period and your lip opening radius. Okay, either diminish or creates more sounding coming out of your mouth or not coming out of your mouth, right? So if you, I don't know if you're a kid, you learn English, right? There's a teacher tells you open your mouth, articulate, right? Because that make more sound out. Okay, you can pronounce that thing better. Okay, so your mouth can actually shape by opening and closing your mouth radius. Okay, that create different sounding. So there are other mathematical form that actually shows. So eventually, you can imagine this is a source, right? Basically signal, right? Systems, right? Source, filter, okay, multiplied by another filter, eventually come out with a signal. Okay, so this is how speech production researchers, speech scientists, right? In the previous days, they try to high levelly trying to analyze the speech production mechanism of human. Okay. Okay, those are complicated, but I want to, again, some take-home message. Okay, these are not the key point of this course, but I think it's understanding some background of this context is important to understand the rest of the signal processing and machine learning tool. So take-home message, complete tool, right? So the final output, right, this thing that you finally use, source, filter, radiation, right? So each one of them can be written if it's as a time domain formula, and you write in a Z transform or Fourier transform. They are essentially three H. Okay, again, source tells you about the vocal opening and closing. Okay, that's voice sound. Okay, voice track shape. Okay, usually means articulator move position at a given time. We call them filter function. Okay, so source and filter. Radiation effect at the lips. Okay, so just remember this kind of source filter model idea of the speech production. So there's some excitation, that's exciting. Okay, the filter function of the vocal tract, and then finally the output. Okay, so the source is basically tells you about how the original signal has been generated, and usually for voice sound we use some kind of periodic signal. For a voice sound we use like random or white noise. The vocal tract system, okay, the filtering function we'll talk about, we'll use OPO model trying to analyze, for example, R, E, U, all this sound. Okay, so that's the OPO model. Radiation effect, we will probably less touch upon this, but essentially the sound is already there. It's more or less how loud it is, how small sound it is. So radiation effect. So continuous speech acoustics signal, one key thing you want to understand is it's highly varied, highly non-stationary. Okay, every analysis or engineering works that we're trying to do on this are basically built on a strong assumptions of every language, every sound unit of a language are being decomposed into a discrete set. Okay, and that discrete set have distinct properties across different sounding units. Okay. And the way we think about them, we think about it as source and filter because of our lung and vocal tract system. Okay, we think about it in that way to be able to design whatever tools that would analyze the actual signal itself. Okay, all these speech structure, they're trying to analyze what happens here. For example, speech recognition or auto speech signal, we're trying to analyze the speech signal and finally record at the microphone output. So the tools we design there are going to be inspired by what we know about speech production, not directly on speech production. Okay, so but these are the concepts you should know what's about the speech production. You should keep in mind the source and filter, all this distinct set of units that we actually make our system work. So Okay, this is a sneak peek into a model of speech production. Okay, many also ongoing work to try to find a realistic speech production. We know in human speech production, it's never just three independent components combined. Okay, there's always a correlation between all these components that somehow affect one another. So in terms of scientific study, there are many people trying to understand really how we do that properly. Okay, for the class, for the engineering application, I'll remember the source and filter model. Okay, if you're we talk about this more from a system and signal perspective. There is a entire study around speech production that actually solve it directly at the differential equation, because these are sounding waveforms. Okay, you can operate entire thing in a continuous domain. Okay, you don't have to discretize everything, makes things simple. Okay, you can actually solve how the waves hit whatever that standing waves would create a different shape, right? From the very first order principles, there's also a lot of people also trying to understand from those perspectives. Okay, so how air actually goes out from around. If we can model the surface, all these structures, we can actually look at it from more physical physics, right? Can look at the movement, the momentum of those waves as it moves across the vocal tract system. Okay, so that's more scientific study of speech production. Nothing really related to speech engineering. Okay, but at this aspect of speech science, I think it's important for us to keep in mind. Okay. So again, continue. Speech, right? We say this is a sequence of sound. Each sound, depending on the characterization of linguistics, it can be source or filters. Okay. So from linguistic form is the smallest meaningful unit of speech. Okay. Now let's rethink about automatic speech recognition system. Okay. We want to have a speech sound, okay, finally turn into a symbol of words. Okay. Now we just say in the middle layer, there's linguistics tells us, okay, every sound, every language has distinct set of sounding units. Okay. It doesn't tell us, there's a distinct set of words. Okay. Written words and sounding words are not the same thing. Okay. So want to make sure the ASR, what it's supposed to do, okay, because it's looking into the sound of that signal, okay, it should map to the sounding units of that of those signals, and take those sounding units, turn them into written words. Okay, so actually these are two-step process happening in the speech recognition system. So again, keep in mind, we call it written spelling, called orthography. Transcription is not the same thing as phonetic transcription. Okay, phonetic transcription tells us this word, right, chocolate pudding, okay, can be written in a particular phonetic structure called chocolate pudding. Okay, but when we hear a sound, right, we want to make it into this thing, but not this thing. Right, so we need another, we call it dictionary. Tell us, okay, this is the written words. Okay, this is its pronunciation. Okay. Then you take your sound, map into your pronunciation, and map it to your transcription. Okay. So just keep this in mind. Okay. What ASR is doing is taking the sounding of the waveform. Okay. Somehow generating what we call orthographic transcriptions. Okay. But the idea we come from speech production and linguistics tells us, okay, there are distinct sets of sounding units. We can write them as I, U, or those spellings. Okay. That spellings are not the same as system. Okay, these two are not one-to-one mapping. Okay, so having this doesn't mean this. So you need to have a dictionary. It tells you every such word has different spelling. So think about this process. That's why I was telling you this can be complicated. Okay, because you may have a word. Okay, that has different spellings. Okay, they are all correct. Okay, you can have multiple spellings, have the multiple sounding, same sounding unit that correspond to different words. That's also possible. Okay. And also what's more complicated is we're taking the speech sound because the way I say the speech, okay, maybe I don't have a good pronunciation. Okay, so the dictionary here does not fit me. Okay. It will fit a dictionary of a foreigner, right? Because maybe the way I say chocolate pudding is not the same way as what the Americans people say chocolate pudding. Okay.
So the dictionary they use here may not be the right dictionary for me to use. Okay, so this can be quite complicated. Okay, that's why automatic speech recognition system at the initial step, they are very modular. Okay, some people work on dictionary of listening. Okay, some people work on pronunciation. Okay, some people work on acoustic sound. Some people work on language. Okay, and of course, nowadays, you don't see this distinction when people run those large models because they try to solve all those things all at once. Okay, within the huge amount of data, they just train it. Okay, so instead of properly design every aspect of this, and they just let the data runs its magic to completely solve the problems of going from all the way to finally the transcriptions. Okay, so that's the most current state of, but the way they do this is because originally they have this process. Okay, this process. So this is the thing we really want. Okay, this is the thing we want the system to output. This is the thing we know the sounding unit, the signal that we record can actually be translated to. Okay, then we also need a dictionary that helps us to map it between the two. Okay. Okay, all these things, these sort of phonetic transcriptions or phonemes, there's some classification, meaning there's some categories of this phoneme we can put in there. They're vowels or consonants. Okay, consonants are created with constriction in the vocal tract, so usually that means it's an unvoiced sound, right? Because unvoiced sound has basically the voice, the sounding basis, the excitation is basic because there's some constriction. So, and it depends on the manner of articulation and place of articulation. You can put consonants. There are about 30 consonants, and then we can look at is the way the configuration interaction of articulator making a speech sound, or the place. Okay, the point of contact where obstruction occurs in the vocal tract between the articulator gesture. So, where the constriction happens and how we move those things, we can characterize the consonants, about 30 consonants, into different categories. Okay, again, just keep this in mind. We won't test you on this, but this is just how people say you have 40 phonemes, you have 10 vowels, you have the rest of the consonants. Depends on manner of articulation, right? Place of articulation, and the point where which point where the air actually creates a constriction. Manner of articulation, how we move those articulation to create a sound. Then you can have different vowels, different categories. Okay, so these are called liquid vowels. Okay, these are fricatives. Okay, these are stopping sounds. Okay, so this is just a nice categorical system for us to understand how the consonants are being placed. What are the distinct properties of those things? Vowels are usually classified based on tongue height, tongue root tension. Okay, like you and stuff. Okay, so a continuant is a sound with a steady state vocal tract configuration. These are a specific set of vowels that's very simple. Okay, those are also one of the few vowels that when you're little, that's the vowels you can start speak okay, because it doesn't require you to change your articulator. Okay, so and also but sound is also somewhat simpler. Okay, so actually it requires a kind of a more complicated movement. So if you always see this debate, right? When your kid first say mama or baba, right? Always say baba. It's not because they know, because it's not because they like you. Okay, it is because ba is relatively easier sound to make. So it's the sound that first come out, and but sound also easy. This articulate movement requires very little practice, and later they start to know how to articulate. They don't say baba anymore, right? They always say mama. It's because they learn how to actually pronounce the right word to the right person. Okay, so every word, because of their manner of articulation, their place of articulation, is also very difficult. So how we learn the language through the process. So anyways, these are all speech production stuff. Okay, just again recap. Source and filter model, right? Source can be voice sound, right, or unvoiced sound. Okay, voice sounds are you weigh all those vowels. Unvoiced sound are those consonants. Okay, voice sound always has a fundamental frequencies. Okay, because it's voiced, because it has these periodic puffs. There's your vocal opening and closing. When you have fundamental frequency, that also means
multiples of those things will also exist in your signal. The harmonics will also exist in your signals, right? Twice the fundamental frequency is also a period. It's also a frequency within your signal. Right? Half of the interval period is also a period in your original signal when you have t is your periodicity. So harmonics also exists. Okay, so your fundamental, when you have voice sound, you have basic frequencies and harmonics of those things. Okay, those are size filters. Okay, your vocal tract. Okay, so creates resonance. Think about its tubes. If it's a voice sound, okay, the filters basically those constriction, place of manner of articulation, those creates a modulations on the white noise. Okay, finally creates a sound of buzz, those kind of sound. Okay, so what we think about this is a source and filter model. If you have a sound that's vowels, you will have fundamental frequencies. That fundamental frequencies can get modulated with some resonance finally with the filter. Okay. Or you have a source, okay, that's like white noise, hit someplace with your manner of articulation, place of articulation having created sound. Because eventually when you record it, it looks something like this. Okay, this is in this thing we all keep in our mind. Okay, we don't know if it's true or not, but we have this concept of how we produce a speech. The only thing we observe is this, right? We just record it and having this time domain signal. All right, because of this concept, let me jump a little bit. Okay, why is this important, right? So let's take this as a time domain signal. Okay, let's plot the a small segment of this and say okay, and then plot it in terms of frequency domain. Okay, just do FFT and plot it. You'll see an FFT magnitude of any small segment looks something like this. Okay, and why we see something like this? Okay, you can start related back. We have source and filter. Okay. So you have this excitation source, right? There's some fundamental frequency, and all the multiples of those things are harmonics, right? So this is your fundamental frequency. Multiples of these things is a frequency. Multiple of these things is a frequency. But you have source multiplied by the filter, right? This is a filter, right? It has a resonance structure. So it has a peak here, it has a peak here, it has a peak here. So when you take a speech sound, okay, a small segment of speech sound, plot is FFT. You don't look always something like this. It seems to have a shape, but it also oscillates. Okay, because you have a excitation source multiplied by a filter or in a communication kind of thing. So you have some carrier wave carrying a message. Okay, it's the same thing, right? So it's an excitation source modulated by the filter, or is this thing and this thing multiplied. Or you have this carrying wave, which is an excitation source, and then carrying a message basically tells you there's a peak here, it's a peak here, it's a peak here. Okay, so you can keep this in mind. We'll basically take this plot and then try to say, okay, if I want to know the sourcing characteristics of the speech sound, what do I do? Okay, if I want to know the filtering function of those things, what do I do? Okay, to make sure the signal, the analysis tool, I can actually properly extract this thing instead of extracting this thing. Okay. So, but if I care about whether this is a male speech or a female speech, maybe I want to do is actually try to estimate the fundamental frequencies. Okay, so I know if it's low, probably it's a male. If it's high, probably it's a female. Okay, so again, depends on what we want to do. Okay, we will design different analysis tool to actually extract this portion or this portion, right? And then, for example, if you imagine automatic speech recognition system, a lot of automatic speech recognition system really cares more about this thing, because it eventually tells you this is an R. Okay, this only tells you this is this is you, right? You male, female, right? It doesn't tell you this is sounding in an R. So, but when the speech sound that comes in is a source exciting a filter, right? We want to get like kind of like the filter out of the signal. Okay, so we can try to get this representation to derive some coefficient as input to our automatic speech recognition system. So we'll design different tools to do that. So it all built based on a very simple concept called source and filter model. In a source and filter model, built on a very simple concept because we simplify human speech production using a long vocal tract system. And then we say this three systems combines each other. Okay. And then we leverage the linguistic knowledge tells us, okay, every language is a distinct set of units of sounding unit you can piece together. Or every sounding unit also has its own different characteristics of producing sound. Okay. Now, as an engineer looking at a signal there in time domain and the frequency domain, then we can start designing tools to say, okay, I want to analyze this shape or this sort of oscillation. Okay, and what are some of the things we can do to properly analyze either the shape or this oscillation? So, just keep those in this mind. Okay, a few more slides and we'll be done today. Okay, so let's go into, those are the background of speech production. Very quick, okay, if you talk to a real speech scientist, they'll say it's way oversimplified, but good enough for us to start engineering mindset. Okay, it's a signal and system kind of mindset. Okay. Understand how we human produces speech. Now we produce that speech, right? Having that acoustic sound, like acoustic signals. Now we started designing tools to analyze acoustic signal in relation to how we understand human produces speech. Okay, so that's the first part of the speech analysis sections of the course. Then later we'll bring in the speech perception kind of analysis, how we know human perceive speech. Then we try to use those knowledge to actually understand what tools to design to process those signals in acoustic space. Okay. So speech analysis topic, we'll talk about, there's some common tools for analyzing speech. We'll talk through each one of them later on, okay? But I want to give an overview of the first one is a short time domain processing. So let's focus on time domain. What can we get from the time domain information? Okay. We'll talk about energy, zero processing, pitch rate estimation. And one key concept I will just state is a short time aspect. Okay, so we always look at a small sounding unit, like a small window of the signal, right? 30 to 40, 30 to 50 milliseconds. Okay, those kind of windows are basic window for analysis. Those are short time. We can do frequency analysis for doing a short time way, so short time Fourier transform. Okay, instead of doing just Fourier transform on entire speech, we take a small segment of speech, do Fourier transform, analyze it, move on to the next window, analyze, move on to the next window. So, and we can analyze the sort in frequency. And then when we talk about these two, what's more important is different parameters you choose in terms of analysis. Say, for example, the window size, how many FFTs you want to see, okay, or this short time, what's the length of that window. It'll show a different behavior of the signal, of the speech signal. So choosing the right parameter for your purpose of studying the speech signal. Because speech signal, now you know there's a sourcing part, there's a filter part. You want to know more about the sourcing part, or you want to know more about the filter part. Okay, so by tuning different parameters, you can show the properties of signal more like the sourcing component, or more like the filtering component. Then later we'll teach one model called linear prediction model. It's a model on the actual filter. Okay. We'll design a set of basically linear filters to approximate that filter functions, and then there's a way to learn. Okay, well at that time they don't call it learn, estimate of the parameters of this linear prediction. So you can imagine this is like a simple linear functions on the filter function we talked about, but we don't know what the coefficients are. Can we estimate from the data? Okay, we'll talk about that, and that can be used as a nice features, okay, for the rest of the speech technology. It can be as input for speech recognition system, it can be input as voice synthesis, and so on and so forth. Okay, so once we have a model of speech, estimated the filter coefficients of the speech function, imagine a source and filter separation, then we can start designing different tools for the rest of the stuff. Okay. So, okay, I'll talk about the short term, and I think I'll be done with that short term stuff. Okay, I'll talk about the short term stuff. Okay. So what short time processing? Okay, is a practical approach for speech analysis. And what is practical? Meaning, speech signal, if you record, do something like this. From your eyes, you can probably see, okay, these are super highly time varying. Okay. Look at this one, completely different. Okay. So if you say, I'll take this entire chunk and do Fourier transform on this, okay, you'll lose the resolution. Okay, you don't know what happens. Okay, maybe here it's faster oscillation, it's slower oscillation. Okay, you take entire this thing. Okay, usually a Fourier transform assumes
the signal you have within there is stationary. Okay, so you give a better representation. But if you do that, split signal is very difficult. So what happens if you go to short time? So you assume by taking a snippet of your signal, within that it's short time stationary. Okay, so it's just a simple engineering hack, right? Just take a little bit. Okay, now because that's so small, nothing has changed too much yet. So we can assume that still it's a short time stationary. So whatever Fourier analysis want to do, all those systems analysis I want to do, it follows those hypothesis assumptions. Okay, so also assume short time stationary. Okay, so it means that the signal properties, okay, remains stationary within that segment. Okay, we won't go into detail of this thing, but if you're interested in stationarity, okay, there's actually a mathematical definition of this thing. Okay, it's not just we say it's stationary, then it's stationary. Okay, so there's actually a truly definition to say, okay, if you assume this signal is a random variables, right, in the process signals, you take that small chunk of segments to the next chunk of segments, that means your mean and the variance, and if you within a small chunk you do autocorrelation, those values don't change across. Okay, that means okay, within that the statistical properties is consistent. Okay. There's a rigorous mathematical definitions of called a white stationary of a random process signal. Okay, if you imagine speech signal is a random process signal, random signal, signal generation, random process. But again, in this class, we can drop it. But if you're interested in saying, okay, whether if you hear people saying their signal is stationary, okay, if you want to be a bad person, say what's the definition? You know the definition. Okay, so, but otherwise, it's more engineering application. We say, okay, take a small segment. We assume properties don't change. What properties? It's actually in mathematics. Is the statistical property. Your mean and variance and autocorrelation structure don't change. Okay? If that remains consistent, that means yes, you are right. Within that segment of the signal, it is stationary. And then it's in a white sense stationary. Okay, then there's other sense of stationary. Okay? If you're interested in this kind of work. Okay. But anyways, practicality, let's take a small segment that becomes a thing. So we call that frame. Okay, frame. You take a window, right? You take n samples out of a frame of a signal, okay, and then you will slide n samples. Okay, so you have n minus n samples that are still overlap. So the thing you create every time you slide a little bit, so that it's more continuous in terms of the properties you actually apply. Okay, so it always maintain this n signal. It's called a short time processing. Yeah. Key thing here is what you do mathematically. What's happening is you obtain a frame by applying a window function, right, to the signal, and you slide those window function. So you slide those window function. So terminology x of n is the signal of interest. In this case, speech. Wn is your windowing function. Frame rate is number of frames per second. So again, one frame every n samples. So that's x divided by n. That's frames per second. One frame equals your signal multiplied by the window function in n minus n. So this frame will lie in the interval of n minus n plus 1 to n point. Okay, so there are n total points here. Okay. Every frame is xn, wn minus n. So n is the window net, n is the n time outside of this interval is 0 value. So when we say short time processing, okay, mathematically what we're doing is applying a window function. And you slide that window function so over time to get each of the small chunk of your signal, and then we'll do the rest of the process. We'll talk about what we do later, but keep this in mind. It's always whatever you do, you first start by saying let's do a short-term processing on speech signal because it's so highly non-stationary. It's one-dimensional signal varying across time, so you always take a small chunk, try to analyze all those small chunks. Later, like I said, we'll talk about the windowing function. In this case, it's important. You probably realize what that extend, right? Multiply by the double. Okay, so your original x, its Fourier representation will be modulated by the Fourier representation of this w. So the signal you actually get out will not be the same as though you have analyzed the original speech signal. So keep all those in mind. We'll understand all these aspects later on.好，我们今天先上到这边，谢谢。